This is PyMol tutorial number 3, and we're going to be talking about images and making publication quality images. So the very first thing, if you are going to be making an image for a paper or for a project, for presentations that you've got, a good thing to do is to write down all the commands that you use in order to prepare that image into a text file, which then, as we saw last week, is effectively a script, which means that if you ever need to reproduce your image, you can just copy and paste your text file into the command bar here of PyMol, and you can go straight back to that original place that you were when you first made the image, which means that you can have a lot of kind of reproducibility in the images that you're making. So it's a good idea, yeah, is to save all of the commands necessary to reproduce those images. So let's just have a quick look here. For example, what we're going to do here is to reinitialize our session, which just blanks the PyMol, and we'll fetch to CHB, and here's our molecule here. Now, I talked to you also last week about these scripts here. So what we can do, I didn't tell you, I don't think, how to run those scripts from the command line, but it's very simple. You can just type the word run and then your script, and PyMol scripts normally have .pml extension there, and this is this particular script here where we're going to make the background white. We're going to extract our ligands or extract our organics, which are normally our ligands, and call that lig. We'll select our backbone atoms, we'll select side chain atoms as described last week, remove the hydrogens and the solvent, hide everything, then show cartoons, show our side chains as sticks, show our ligands as sticks, colour everything by their chain name, colour our ligands black, colour all of the non-carbon atoms by non-carbon colours, and then orient around our backbone and select nothing. So because this is in the same directory that I'm in, I can just say run this, and here is the application of those particular commands as we saw last week. So when we're going to start making images, a lot of the time you don't particularly want to just use, again, if you use this orient, I'll type it up here, orient, what that normally does is it centers around any symmetry axis, the highest order symmetry axis that you have in the molecule. So you can see here we're looking down the Z plane of the pentamer axis here. And it's kind of useful as an overview, but maybe you want to be looking at something nice, and a nice specific interaction, for example this ligand over here, and you've spent some time and effort in deciding exactly how you want to position the camera, and then you go away, you make your image, and someone comes back to you and says, actually I think this should be this color, and maybe we want to be doing something very slightly different, and you need to come back and replicate that same image. That can be a little bit difficult. So I'd just like to introduce you to this command here, which is called getView. If you type in getView into the command bar here, the result of getView is that it outputs here something called setView. And what this does is it gives you the coordinates of the camera, the lighting, the distance of the zoom, the control of the Z-plane clipping, and all of that kind of information in order to recreate this exact view that we have here if we were to go somewhere completely different. For example, we can copy and paste this back in, and that returns us back to that initial place that we were at. So for example, if we've got in some parameters here to identify hydrogen bonds between our backbones and our side chains, and we found that we had a nice view that we liked, we can always return to that view very easily, and then we can apply the changes that were asked to be made to it. So I thought I'd introduce that as the first point, because this is a really easy way to recreate your images. So talking about some specifics, there's two basic ways in which you can generate images. I mean, for example, you can just save this as an image, right? We can go to File, Export Image as a PNG. But I don't know how the resolution of the video comes through on Teams here. But you might be able to see that there's a kind of sawtooth edge to some of these images, some of these lines in the images here. And what does mode 2 denote? Mode 2 denotes that we're looking specifically for hydrogen bonds. We're not just trying to measure the distance of any atom between any other atom. Yeah, so mode 2 is saying we're only looking at hydrogen bonding interactions. So there's two basic ways. Again, I'm not sure if you can, maybe I can angle the screen in such a way that we can see this sawtooth edge. I don't know if you can see this on Teams here, but we have this kind of sawtooth edging here. And this is all to do with something called anti-aliasing, which is to do with having a nice quality pictures. And in order to apply anti-aliasing, well, what we can do is, I'm also going to introduce you to another thing, sorry, called get. And what you can do is say get, and then have a function or an option. And what Pymol will do is it will return to you after you've said get anti-alias. It will say, well, your anti-alias is currently at 1. And if we use the keyword here, draw, I don't know, this probably isn't coming through on Teams, but on my screen certainly this diagonal line here is actually just 4 straight lines that have been sawtoothed. And if I do draw, then it becomes a lot smoother. What I can do is, instead of saying get anti-alias, I can say set anti-alias and make that 2, so that now the anti-alias setting is higher. And now if I use draw again, I now have a really nice smooth edge to my lines here. Try that on your own version of Pymol and you'll see that this is very good. Of course, the higher the anti-aliasing, I think it only goes up to 2, but if you're on the anti-aliasing of 2 and you're putting in various other functions as well, then that starts to eat into your kind of CPU time for generating these images. And when you're doing very basic things like using draw, then the anti-alias, then the amount of time it takes your CPU to render these things isn't particularly difficult. What we can do is, after we've done, well, if draw is not very impressive, which to be honest it isn't that impressive, because all that it really does is apply the anti-aliasing, what people will generally use is the command called ray when they're making their images. And if you do ray, it takes a little bit of rendering time here, but what we're also going to do is apply reflections and shadows and things like that. And we should see, okay, you can see here we've got shadows now inside the helix, shadows cast onto this beta sheet here. It puts on our alpha checker so that our alpha channel is white, which means that basically all things in here that are white are transparent. Yeah, so what we can also do is we can say ray x versus y. So at the moment when you hit ray, you ray according to the dimensions of your window. So if you have a small window and you hit ray, then you'll have a low resolution image. But if you have a very large window and press ray, you'll have a higher quality image. But that's all a little bit arbitrary. And you can open Pymol, or when you open Pymol, you can set its window size. But it's kind of unnecessary to do that. So what you can do instead is give the ray x and y dimensions here. So we can say we want a ray 2400, 2400. Okay, there we go. So now this has been ray 2400, 2400, and it's given us this nice square box here. You can abbreviate this to just ray 2400, and that will put 2400 in both dimensions. I won't bother doing this because you can see that took about 30 seconds to render, but we can ray 1200 to 2400 and get oblongs rather than squares, or whatever kind of dimensions you're interested in getting by doing these guys. There is a nice website called Publication Quality Images that I've given you the link to here, and effectively I'm now just going to go through some of the things that it says on there. So for example, this ray command, these ray values 2400, 2400, is really your inches times your dots per inch, right? Is what that ray value is. So if we did ray 576, 576, and then we save that image, you can save an image by saying save, and then so long as you append it with PNG, it will know that you're trying to save an image, and it will just save that image for you. Now if we took that image that we saved and we made it 8 inches by 8 inches, then it will have a DPI of 72, right? And correspondingly that works for obviously for any of these parameters here. And a general safe bet to go for is 2400 for your very top quality images, because again, if you've got an 8-inch image there, then you've got a DPI of 300, which is plenty for most people's needs, really. Now, I did have a little comparison here of what these things look like. So this is when you ray 576, 800 or 2400, you can see that really the resolution is the same. So the image gets, sorry, the resolution isn't the same, but the image basically gets bigger as you increase the number. And therefore, if you take the same portion of each of these images and you expand them, you can see here that really at 576, it's the quality is pretty bad. But getting up to 2400, when you zoom into these very, very tight sections here, we're still retaining pretty decent image quality there. So what I would generally do when I'm making an image is to ray 2400, and then I'd export it into either GIMP, Fiji, Inkscape, whatever your Photoshop, whatever your kind of image processing software of choice is. There's an alternative way that you can set your DPI, and that is by using the command called PNG. You do PNG followed by your file name, whatever you want that to be, and then the DPI that you choose to have. And this is kind of almost the opposite of doing the ray command, because here, of course, the larger the dots per inch, the smaller our picture is, because there's more pixels compressed into that space. And if we expand the same area of each of these, you can see that the resolution of all of them is identical, because it's already been rayed. So and of course, sorry, what you can also do here then is, using this PNG command, you can combine both, where you can define which height and width you want, and to have your DPI, and to say that you want to ray it. But long story short, I'd always ray 2400, then stick it into your image manipulation program and have a go with that. Raying can take a long time, so let's just have an example of this. We'll go back to something pretty complicated here, and I might as well start ray now. So when you've got something large and complicated, something that has an interior, of course, when you're hitting the ray from various different light points, and what we can see is that while we're going here, we've got our CPU here, which is getting maxed out, but we're using a correspondingly small amount of our memory while we're processing our images, and that is not very efficient, because actually what we can do is we can ask Pymol to allocate more memory into our processing, and therefore relieve some time on our CPU. And we do that using this command here called hashmax. There we are. So yeah, we can say get hashmax. Oh, and it's saying hashmax here is equal to 100. So now that we know what it is, maybe we can set it to something else. And we can see here we took 64 seconds in order to make that ray here. So we can set our hashmax to a larger value. We can hit ray again. Now this time here, you can see that correspondingly we're using a little bit more memory than we used last time, but not substantially more. And I guess we'll just have to wait. Ah, there we are, look, 21 seconds. So that's like 3 times quicker. So we can set ourselves to a hashmax of 400 and ray that. And now again, correspondingly, you can see that our memory usage has gone up even further. And hopefully it's going to take even less than 21 seconds. There we are, 15 seconds. Great. and then you could even try 800. Array that. Now, what can happen if you set your hash max too high and you peak out your memory here, Pymol will just crash. So it's a good idea to find and do a little bit of a test to see which of these hash maxes, one, don't stop your computer from working or stop Pymol from or make Pymol crash, but also you can see here for whatever reason allocating more memory to here was a slower process than allocating more. So actually this was a nice little sweet spot here where the CPU and memory allocation was nice. So for me, setting hash max 400 looks like it's a pretty good thing to do. For you, it will be a different value on your computers, so it's worth, especially if we're going to be talking about making movies next week, and if you want to ray each image of your movie, then you can really start to get into long processing times for these. So it's worth having a quick look at what your hash max can be and setting that to something optimal for your system. So let's talk about a few of the effects. There are a lot of different effects when it comes to making images. We'll just bring in one NQU. I've used my little setup script that I showed you earlier, set my hash max and deselected things. So we can ray this, and we get some default options, such as the background is opaque, we have shadows cast, there's a certain reflections and Q depths which are activated, and we can use this get command here in front of our options in order to get Pymol to tell us what each of these different settings are at. What we can also do is, whenever you're doing any programming, you can often use the tab button in order to do an autocomplete. So what we can do is say get ray and then hit the tab button, and here are now a whole list of the different ray options. Now each of these you could stick into Google and you could find out exactly what they do and how to manipulate them in order to do various different bits of processing. And so really for the rest of this session I'm just going to talk about a few of those things. For example, we can turn off our reflections and our shadows and make our background opaque and take away our fog, and then we can hit ray again, and to be honest there won't really be much of a difference here, but we'll just have the opaque background, no shadows. Makes, it might be a cleaner view if you're interested in that. Now some of these you can really mess up your images if you select the wrong things, the wrong options for them, and I'll show you an example of that later. But someone has gone along and made some predefined modes that you can select here. So what we can do is we can use the get command so that we can find out what ray trace mode we're in. At the moment we're in ray trace mode 0. So what we can then do is set ray trace mode to 1, and then we can hit ray, and you can see you can have this particular option. Now here we've got thicker black lines. It's a bit more kind of cartoony, I guess, and this can often be quite nice if you're kind of I think if you're zoomed into areas, it can add some definition. Yeah, you can see it's just a little bit kind of more cartoony. You notice actually that here the lines kind of almost appear a bit thinner, but I think really the lines are at the same thickness regardless of how zoomed in or out you are. So if you're very zoomed out, for example, I think then the line thickness stays really quite thick. It's also dependent on your resolution. So if you ray at a high resolution, then your line thickness becomes thinner. But you can play around with all of these options in Pymol. For example, there's this option called ray trace gain, and we can see here we can find out what its default setting is here, and we can set it to something a little bit different, or we can set it to something really quite ridiculous, and then we can hit ray, and you see that we can manipulate the even just the line thickness that surrounds each of our guys. So So there's lots of different ways in which you can play around here. There is, just in case I'll reinitialize, just in case I've changed the options there, but there's also Ray Trace Mode 2, and if you go on to this one, it gives you a kind of, I think it's a black and white version of it. Yep, and again, if we ray 2400, we'll see that the thickness of the lines is again dependent on the resolution, not on the level of zoom. So here you can see that we've got these thinner lines than we had before. Might be important to you, might not be. There's also Ray Trace Mode 3. Now here you can see that we've there's not a lot of smoothing in the colours, slightly artistic representation of the molecules, and it kind of even more cartoony. So I guess Ray Trace Mode 0 is the least manipulated or cartoonified, and as you go through these different ray tracing modes, they add a bit of different dimensions to the images. So we can manipulate all of our different parts of our structure here. So for example, we'll just bring in a new session here. Let's just show everything as sticks, and then here we can get the valence. Here we have our valence on, and what we can do is we can set our valence off, for example. Let's try that again. Okay, for whatever reason that now has worked. You can see that our double bonds have been removed here. So this is just, I'm showing you this just as a way to say, one, you can manipulate things like your stick radius. Why would you ever want to do that? Well, this just depends on exactly how you want to look at your images. We've set our valence to 0 already. We can colour all of our things by chain, and maybe this is a representation that you kind of quite like. You can see that it's almost a bit like a kind of licorice kind of look. I think it's called, where you've got really your bonds are basically the size of your corresponding atoms. And again, it's kind of like a different kind of stylized view of your molecule, where maybe it's easier to see certain features of your protein in this view than it is in the more complicated views. And again, obviously you can set your stick radius to whatever you want, make it a bit chunkier if you feel that way. You could also, of course, to set your stick radius, you can of course set your sphere scale as well. So if you like to look at your protein in the sphere view, yep, you can change the sphere radius. A lot of people do prefer the cartoon mode because obviously there's a lot of intrinsic information in the cartoon mode, and of course you've got control over all of the different aspects of how your cartoon looks. For example, you can show your entire cartoon simply as loops. Let's say, sorry, as cartoon. So this is your cartoon as loops. You can then also, if you choose to, show the entire thing as these kind of rectangular view, or the whole thing as alpha helices, or the whole thing as kind of fatter tubes. And of course, if you ever get lost, you can just go back to say cartoon automatic. You can also redefine parts of the secondary structure. For example, if for one, it may not be correctly allocated, or you might be doing something where you want to play around with that. So here we can choose an alpha helix, for example, and we can use this alter command, which I think I showed to you before. But this time here, what we're doing is we're defining our secondary structure as a loop, and we can hit that, and now we need to just basically rebuild our image. And then this time here, what we've done is we've made this into a loop rather than a helix. Some people quite like, you might see in some journals, these fancy helices where it puts a little cap on it. You can do this, and again, if we were to go to get, or in fact set cartoon and then hit tab a few times, here it brings in a whole bunch of the different cartoon options that we can mess around with. Okay, so that's looking at cartoons and sticks. Some people want to have a nice kind of topological view, if you want a kind of very simplistic view of your protein. So for example, we can just set that as cartoon. We can color our helices, our sheets and our loops in different colors, and then we can set smooth loops. So what this does, if you see this jangly line of your loop here, if we set smooth loops, it just makes all of these into less complicated loop structures in order not to detract from the basic topology. And then you've got the flat sheets here, which actually are more appropriate for a topological one, but you can also make those sheets into a more backbone tracing, because the sheets are generally don't actually trace the backbone completely. They make an average of it. So there's lots of options like this that you can go through. Surfaces. If you're interested in surfaces, how can we manipulate those? Well, let's have a quick look. Let's fetch in this guy, remove our solvent, orient. We'll get our topological colors on there again. Here's a particular view to have a look at. Oh, well actually what we'll do, sorry, set surface. There's our surface, and then I'm just going to zoom into this particular little lump here. So we can set our hash max here, and then we can rate. It will take a bit of time, and you can see that it looks a bit chunky and doesn't particularly look particularly nice. But there's a few things that we can do here. For example, option called spec power, and we can see where that is at the moment, and that is at -1. So we can turn that on, give it some value here, and now if we rate, I don't know, this one isn't hugely noticeable, but what happens here is that we've tightened up the reflections in these white parts here. There's another one called spec reflections, and that's currently -1. -1 is always the default, but of course we can set it with other values of choice. Now what this does is it kind of expands the reflections while keeping them kind of defined with the spec power. So if we do this now, you can see we've got a much more of a glossy surface than we had, but the resolution of our surface is still pretty rubbish. And there's a command here called surface quality. We can see what that currently is 1. The surface quality, we completely re-render the molecule, so this can often take a bit of time to complete, but once it's done, it's done. And what we do is while this is going, I might as well talk about how that works. So you can set this solvent radius. It's normally at 1.4, which is the radius of a water molecule. And what we're effectively doing is rolling a water molecule all over the surface here and showing the interaction between our water molecule that we've rolled over the surface and our protein. And obviously the resolution at which we do that rolling of the water molecule over the surface is dependent upon the surface quality. So here now you can see that our surface is rendered a lot nicer, and we can hit ray, which will probably take a bit longer this time because it's got a bit more work to do. But with these spec reflections and the spec power here, you can see we end up with this kind of nice glossy smooth surface. Maybe this particular angle wasn't a good one to look at, but yep. So if you're into showing your surfaces like that, then that's a good one to do. So now I just thought there's not really too much more to go into here, but what I thought I'd do is go over a few examples just to give you guys an idea of the things that you can and can't do, or well, the things that you can do. Sorry, so there's a nice website here that you've got a link for, which just goes through a bunch of different ways of doing various different things. So I will go through some of those options now. So a nice one when you're looking at a molecule is to maybe you're interested in the hydrophobic sections of your molecule. So what we'll do is we'll start a new session, set our hash max, bring in our protein. We'll just make it grey. If you remember from last week, we were using all of our different selection nomenclatures here. So here we're going to make a selection that we're going to name that hydrophobes, and we're going to pick all residues that are alanines, glycines, valines, isoleucines, leucines, phenylalanines, methionines. We'll show all of those as spheres, and we'll also, but not their backbone atoms, although we will include their carbon alpha atoms. And then all those hydrophobes that we had, we're going to make them orange. Disable just means to unselect. And then we'll show the surface of the polymer, make it transparent, and make our organic molecule, our small molecules, sticks and black. And that gives us this kind of nice see-through representation of our molecule here, where you can see that actually largely the surface are hydrophilic, but all of our proteins have these kind of dense hydrophobic cores in the middle. So that's pretty good. And say we're interested in looking at our ligand. Here's a nice saved view that I had for the ligand of interest. And then we can mess around with this spec power and this spec reflection as we did before. Find out what their defaults are before we start messing them around. We can make a new selection, and if you're not very careful with your selection, you can end up making something which is not particularly good. So be careful with how you set these things. Here's an example of some good settings. I will do all of these. I'll do these two here, but I won't do the surface quality 2 because that will take a lot of time. And it says here, don't do this. And the only reason for me, this is for me not to do this. You should not do this one yourself because that's a rubbish selection of options. But this is for me not to do this one just because it takes too long to render. But I should be able to have an image here of a nice kind of glossy, shiny surface structure that's obviously got this transparency, and you can see all the hydrophobes in there, and then this little greasy pocket that the organic molecule is fitting into. We can make slices. Now this goes into a little bit of Python coding here. So we'll just reinitialize our session here. So here we're going to talk about things like Q depth and the clipping plane. So the clipping plane is what we control on the mouse wheel, but of course we can also just code in some control for that here. So let's set these as 0, so that takes away all of our fog there. Now this section here is really, this section here is a bit of Python coding really. So this is just making a variable. So we're going to create a variable called fraction, which we're going to set at 0.2. We're going to create another variable here called view, which is going to be the command called getView, and I showed you the getView command before. If we get view, you can see that the getView here is a matrix of various different numbers here. So then we make another variable here called near distance, where this equals our fraction that we've defined by the 16th and 15th variable of our getView matrix, and so on and so forth. So here we're just making some definitions, some variables here that we can call on in the future. And then what we can do is set our surface. This is a nice option here called set ray color interior. This doesn't do anything until you hit ray. We'll make the background opaque, set the surface color white, and then we'll hit ray, and you can see what the interior does here. So instead of showing a hollow interior, it kind of fills the interior like a cake that you've sliced open. And then we can save that. And then we can apply some of these clipping effects that we defined earlier to look at a slightly different section. Now just look at the cartoon, unset the opaque background, and hit the ray again. And then this just gives us a bit of our cartoon model. And then you can save both of those guys independently, and then you can open up your editor of choice, and you can bring in your two sections here that you've got, and then you can combine them together, and you can get again a different representation of a different way of, or style of looking at your molecule that might be of interest to whatever it is that you're studying. Binding pocket representations, these are always, I think, things that people are hopefully interested in seeing. So we'll reinitialize our session, bring in our molecule, set our hash max, remove our solvent because we're not that interesting. Here we'll extract some new objects. So we'll extract the protein, which is our polymer, the ligand, which is our organics. We'll define our backbones and our side chains as independent selections, and then we'll show those as cartoons and sticks respectively. Color our chains, color our sticks. From our organics, we'll just select the chain A ligand to look at, and we'll call that lig1. And then we're going to use this set surface carve here. So what this does is it means that when we're setting a surface, we're going to set that surface within certain restrictions. So we're going to carve at 4.5 angstroms around the ligand 1, and frankly I'm not quite sure what this option here does, but we can stick those in. That doesn't really do anything until we show a surface. So what we're going to do here is show a surface, and we're going to set that surface on our protein within 8 angstroms of ligand 1. Now this kind of works in consort with this one here. You can just use this option, but this makes a higher refinement of where that surface gets cropped. So we can do that. We can make that. You can see the surface over here, right? That we've cropped only that surface that's close to our ligand, and then of course we can set some lighting on either side of that surface, make it transparent, orient around it, and zoom in. And here you can see some nice stacking and pocket interactions there. And if you want to go even further, you can set your surface type to surface type 2. This makes it into a mesh rather than a surface, and maybe as a mesh it might be nicer in a white color. And then maybe we're interested in looking at some hydrogen bonds and such things. So that's just some ideas there for looking at pockets and the kind of options that you might want. I'm not quite sure what this is, but a slightly more zoomed out version. Okay, I think actually with the alpha checker on here, it means that you can't really see the pocket very well. But I showed you there was a program called QtMol, and again, just to emphasize the fact that in PyMol there are a lot of ways in which you can manipulate your images. We can recreate these kind of QtMol images, so just going to make a new session here, and then this is another way of setting colors. So you can set colors for oxygens and then give them RGB values, and for the nitrogen we'll do that. We can set spheres for everything. This is another one of these util functions like CBC and CNC. I can't quite remember what that one does, but that can always get googled. Set the background white, and then here we're setting a bunch of lighting options. Some of these we kind of saw earlier. Some of these are new. I'm not going to go into these. I don't really know a lot about these, but this is more just for an example. So we can set those options, and we can end up with a molecule that looks a bit like this. And then when we ray it, we should get all of those fancy features that we've defined here, where you can see that now it's a very different looking kind of molecule. This is really just to emphasize that there's lots of different ways in which you can manipulate these images. There's a guy called David Goodsell. He does a lot of water paintings of water pictures of of molecules. So you can also kind of recreate some of the David Goodsell like imagery by let's just I'll just do the whole lot. There we are. Yep, and so there we go. That's another example. You can Google and find lots of different examples of ways to manipulate images, but the most essential part really is this Ray 2400, and then just manipulating it in your image package of choice. But be aware that there are many different ways in which you can stylize your images, and of course the reason to stylize the images is to convey the point that you're trying to make. Showing the cartoon structure all the time isn't always the best way of conveying like a ligand binding site, for example. Even here you can see that we've got this kind of contrast between the ligand and the protein, and you can see various interactions here. So think about what it is that you're trying to say with your image, and then choose something that's appropriate for that. And that, I think, is the end of what I wanted to talk about today.